This is my video report for Lab 2. In this lab, I investigated the electric force between two charged tapes, modeled them as lines of charge, and compared the results to a point charge model from Lab 1. The purpose of this lab was to model two charged tapes as lines of charge and calculate the electric force between them. The key physics principles involved are Coulomb's law, electric fields, and gravitational force. By the end of this video, you'll see that the charge required for the tapes to float is approximately 1 microcoulomb. In the experiment, I used two charged tapes, each with a mass of 1 gram and a length of 20 centimeters. The tapes were placed 5 centimeters apart, and I observed the conditions under which one tape floated above the other. The gravitational force on the tape was calculated using Newton's law, and the electric force is modeled using Coulomb's law. To model the tapes, I used a computational model in GlowScript. The tapes were represented as lines of charge with the charge evenly distributed along their length. The code calculates the electric field at each point on the top tape due to the bottom tape and sums up the forces to determine the net electric force. The results show that the charge required for the tapes to float is approximately 1 microcoulomb in the line charge model compared to the 0.74 microcoulombs in the point charge model. The electric force calculated using the line charge model is 3.6 newtons, which is more realistic than the 9.99 newtons from the point charge model. In this model, I made several assumptions. I ignored air resistance, assumed the charge is evenly distributed along the tape, and treated the tapes as perfectly parallel and horizontal. These assumptions simplify the calculations, but still provide a good approximation of the real-world behavior. The line charge model is more accurate than the point charge model because it accounts for the distributed nature of the charge. The point charge model overestimates the electric force because it assumes all the charge is concentrated at a single point. This explains why the charge calculated in Lab 1 was lower than in Lab 2. If I had modeled the tapes as point charges, the charge required for the floating would be underestimated. The estimates differ because the point charge model ignores the distributed nature of the charge. The line charge model's results of 1 microcoulomb is more accurate because it accounts for this distribution. In conclusion, the charge required for the tapes to float is approximately 1 microcoulomb. The line charge model is more accurate than the point charge model because it accounts for the distributed nature of the charge. This lab demonstrates the importance of using appropriate models to describe physical phenomena. Finally, I would like to acknowledge the resources and tools used in this experiment, including GlowScript for coding and the lab instructions provided by my course. Thank you for watching.